So, welcome everybody. Robin Passama, not Rubin Passama, apparently. So I'm a research engineer in the Liam laboratory in Montpellier. Today I will try to do a kind of experimental presentation. I never did this, but I will try to give you an overview of the work we are doing at Liam. And I try to put all those very different work into a common framework because we have, well, some ideas of what the future could be, and so we try to go through this path. And I will try to give you what we try to do concerning robot programming at eye level. And this is so why I give this title to the presentation. It's Programming a Robot by Teaching, so our work in progress. And I also try to put some explanation of what I understand of the cloud computing and how this cloud technology can help us implement this scenario. So this is the outline. So first I will give you an introduction just to explain the context and concepts. Then I will present a very simple scenario, and then I will try to show you what we are doing in my laboratory to implement every needed, required skill used to implement this scenario. Of course, this is still science fiction for now, but we are doing research, so we try to do things that may be useful in maybe 10 years. We don't know. And in the same time, I will also try to give some clue of how to use cloud to solve some problems in this process. And finally, I will give a little conclusion. Okay, so what is programming a cobot by teaching? So cobot, maybe an explanation. Cobot is the contraction of collaborative robot. Okay, so I will use cobot for short. So the basic idea is to allow robots to work very near to the human. So the basic principle is to allow a worker, so someone that is really not an expert in robotics, to program a robot at a very high level. So using, for instance, so you can use directed operation. I believe you know what it is. So you use devices to directly control robot movements, or using physical human-robot interaction. So by just taking the robot and make it move by using your hands, for instance. And we can also use some specific dialects to dialogue with the robot. For instance, you can use voice, but we will see that we use another mean. And you can also try to use augmented reality system to, maybe perform some specific action with a robot. Okay, so now, why is it useful for? It's a good question, because hopefully for now there is no real application, so we can do research on that. But the industry try to implement a process where the plans can be reconfigured very quickly. So you have to know that for now, a plant can take weeks or months to be reconfigured. Okay, once you change the production, the process, you need to reprogram all the robots, to change the environment, etc., etc. So it's very, very, very long process, and of course the cost is very, very high. So the new paradigm is to be able to reconfigure very quickly the plants, but you can apply this to many different areas. You can think about an hospital, for instance. It's mostly the same idea of the hospital 4.0 scenario. Okay, so what is the robot useful for in this process? Well, we imagine that, at least for next years, the robot will be in charge of very simple tasks, okay? And the human will have to do some very difficult tasks for the robot, for instance, everything related to perception and understanding. and also for everything that we consider as with a very high added value. So there are, for instance, in plants like in the car industry, you have people wiring the cars this is a very difficult task, and we just don't know how to do that with a robot for now. And these people are very skilled, and we don't imagine that we can change this in the next years, and that's a good news for them. So, when we will use this? Well, anywhere, anytime we want to change the process, or either there are new products, or you want to improve the performance of a plant, or generally a process. So now, okay, we want to do this, but how to do this with robots? Obviously, for now, robots are not versatile enough to implement this idea. We need robots that are capable of adapting to the different configuration of the plants, of the different tasks it has to accomplish. So it's not already something that exists in the industry. Robots are mostly very specific to the task they have to do. And of course, you need something that is easily programmable, contrary to current situation. You need to be able to, if you want to reconfigure, let's say, each week a plant, then you need means to program very quickly and in a very robust way your new process, okay, with using a robot. And to do this, we need versatile robot with three main abilities. So the mobility, capability to move in the environment, some abilities to manipulate objects, and very different objects, and of course you need high-level perception of the environment. So the robot has to not to understand, but it has to know and how to detect objects, how to localize in the environment, etc., etc. So now, considering this very general presentation, I just try to give you a very simple scenario and how it can be implemented. So first of all, of course, I present our reference platform that is called Bazaar. So it's an humanoid-like robot. Of course, it has no legs simply because using legs is a bit constraining because you have to ensure stability, and of course humanoid robots most of the time fall. So we just want to avoid this and have a very stable robot. That's why we use an omnidirectional platform. This is really sufficient for what we want to demonstrate. So the omnidirectional platform is equipped with leaders, and we also mount two arms, 7-DOF arms, and with dexterous hands mounted on top of these arms. And also we added 4 sensors, 64 sensors in the wrist of the robot. And more recently, we also had a vision system that is a bit more evolved than the two cameras you can see on the picture. But this is not print now. But we put a Kinect sensors, and we are capable of moving it with a palm tilt unit. So maybe just a word about that. Also yes, I forgot there are touch sensing sensor in the fingers. Okay, so here you can see that this is what we imagine. Yes.
How much does it cost?
A lot. A lot. No, a lot. Very expensive. So more than 600 kilo euros. 600 kilo euros. Yes. Everything. Okay. I speak about the cost when you buy them.
Yeah.
Okay, of course, because in fact what we did is we buy each element time after time.
It's not a commercial product.
No, not at all. We mounted it. Well, we assembled all the parts. So these are KUKA arms. The hands are shadow hands. The mobile platform is from Neobotics, etc., etc. So we mostly design no parts, okay, of the robot except pieces at the interface, okay, just to be able to mount, for instance, the 4 sensors on the arms, etc., etc.
So is it possible to use it in a hospital, for example, assisting?
Excuse me.
Is it possible to use this platform in a hospital?
This one in a hospital? No, I don't recommend this because obviously I think that people will be really afraid of things this in an hospital. We have another robot that yes, that has been designed by at least the upper part has been designed by the COA, it's a French institution, and we imagine to be capable of using this other robot in the context of an hospital because it's mechanically compliant. Okay, it's a cable robot, 2-arm cable robot.
Mm-hmm.
But yes, no, I admit that this one cannot be used in an hospital at all. But well, maybe a last word. But you can. The problem is more to see what are the capabilities of the robot. In fact, the robot's parts used are not so important. Of course, you need high quality robotic parts, but it's not that important. You need manipulation capabilities, mobility, and perception. That's it. You can reproduce it with maybe a less costly elements. Okay, so now this robot is well, or will be used in a scenario, and so I just want to present you this scenario in a very simple way. So we have here a plant, or more probably a part of a plant, and in this plant you have shelves, okay, where the robot can take some elements, some product parts, a workbench where here in red, where the parts are assembled to create an object, then a station where a human operator can inspect the result, because for now at least most of these things are really difficult to automate. It's very, very difficult, and most of the time industrial companies want a human to check the result of an assembly. So for now I cannot imagine that it can be automated by a robot. At least it's a question of confidence. Now it's difficult for these companies to have sufficiently big confidence in the robotic system to let it decide whether or not the object is well assembled or not. And then finally you have 2 conveyors, one that brings the object, if it's okay, if the object is well assembled, it brings the object to the next step of the industrial process. Otherwise there is a disposal conveyor to, well, bring the object, we don't know where, in a bin maybe, I don't know. So now the scenario is this one. So we want basically, so the robot knows nothing, maybe except the map or organization map, maybe it can have that. But here the principle is that first the robot will go to the shelf and take parts, to go to the workbench, then put the object on top of the workbench and try to assemble them. Finally, once the object is assembled, go to step 3 and wait human decision to know whether the object is good or not. And finally, go to the adequate conveyor depending on the human decision. And finally, do the cycle again. Repeat this operation cyclically. Okay, basic. Already, even if we want to teach the robot, okay, we want to program each action, we already need a lot of things that are related to robot autonomy, in fact. So robot must implement a lot of things internally. It's not just, okay, directly teleoperating it in the system and position it every joint. So it needs to be able to at least localize and optimally map the environment. Of course, at any time, it needs to ensure that the safety constraints are respected. And during this process, we will see that it also needs to detect and why not interpret human movements. And of course, if the robot needs to manipulate objects, it needs to be able to, well, we need it to be capable of detecting the objects, okay? So it needs to take a box, it needs to detect this box, okay, basic. Okay. So, what can we do to teach it what to do? So this is what we focus on at Liam. Okay, so we focus very specifically on physical human-robot interaction, but also coupling it with vision. This PHRI is a mean. We have also vision that is really mandatory to have good estimation of the environment. But we can also use other techniques like what we call embodiment. So it's a really nice word to say that we will do direct operation with visual feedback directly to the operator. So the main idea is to allow the person to be in the robot corpse. Okay. So this is something we just started to study at Liam. But maybe it's something really promising for very specific tasks. Not all tasks, but for some specific tasks, it's something that I believe it will be really useful. And okay, so these are the basic means, and then we also need to specify the task sequence. Okay, we just want to give, for instance, the robot, okay, go to this position, so a waypoint, or take the contacts on these objects. So you need to specify the contacts relative to the object. But okay, we can learn it with the means I already presented, but okay, we also need to say, okay, that's it. Now you know the target. You know the target pose, the target force, the target contacts, etc. And so to do this, we need something to speak, to dialogue with the robot. Okay, and we are studying more specifically everything related to human gestures. Okay, so we want to interpret human gesture and bound these gestures to specific learning actions. Of course, related to embodiment, we can use AR devices like glasses and gloves with to get haptic feedback, etc., etc. Also, maybe we can use these devices, this AR device, to maybe program some things in a kind of virtual environment, Minority Report film. Well, you can see what kind of interface I'm speaking about. Okay, now of course we can imagine we define every step of the mission. So here the round are atomic, but the inside you may have many different tasks, of course. The sequence can be, of course, far more complicated than this one. And now we need to execute the mission. Okay, so simple. We can say, okay, it's simple. No, not that simple, because we need to add extra degree of autonomy to the robot. So it must be capable of navigating in the environment. So all those other degrees of liberty, of autonomy are already managed. We need to manage them, and we need to manage other degrees of autonomy. So it's about autonomous navigation in the environment, because in the first time it just followed the human, but in the second it needs to act by itself. And of course we need autonomous manipulation capabilities. Okay, because the operator will not be aside of the robot and will not any time help it to grasp things. So it needs really autonomous manipulation capabilities. Okay, so just now imagine we have this sequence. The problem is that executing the mission is not replaying a sequence. Okay, we just don't say, okay, do that, then do that at any time. We don't have a plan that define what the robot must do at any time. We just have objectives, okay? Different sequence of objectives in the environment, and the robot needs to translate the sequence of objectives into a sequence of activated skills. so what I name skills. This is a basic functionality implemented in the robot control system. For instance, ability to reach a contact, ability to move, to localize, to map, to everything. Okay, every basic action we can consider in a mission. And when you consider that, of course, you have, okay, let's suppose we can derive from this very high-level sequence of objectives into a sequence of robot skill activation. We also have to take into consideration some other criteria, like performance, what we call performance criteria. So this is about basically what we are currently studying is the minimization of energy. Okay, so the robot has to minimize his energy just to do the mission. Of course, the goal is to do the mission, okay, anytime. But once you consider this, then you can do this with the minimum energy required. And you have to minimize also the time of the mission, or at least you have to do this in a predefined cycle time. At worst, in a given amount of time that has been defined, for instance, by someone, by the operator, or who knows. And of course, also we need to guarantee some performance criteria. And the most important one is safety. Okay, we don't want to hurt any people in an environment. We don't want to break the robot. We don't want to break objects. So anytime we need to ensure a lot of safety constraints. And finally, in addition to all of that, we also need to guarantee, well, to manage faults that may appear in a mission, during a mission. So basically, you can think of a sensor failure, for instance. Okay, so your LiDAR is giving you just stupid data. Okay, so very noisy data, or we don't know. So you need to be able to diagnose those errors. Also, so the basic idea is to know that there is a fault, and then once you know, you have to react. Okay, but of course, you have to imagine that any fault on the hardware, for instance, or even in a software, can impact all the skills that have been used to execute the mission. So there is a kind of we need to reconsider the planning, the mission planning, the sequence of skills, and modify it to manage this fault, for instance. Okay, so use another sensor. So this requires that we have redundancy in the sensors available on the robot. Okay, so I now put the problem, and I will try to show you what we're doing at Liam, just to solve some of these points. But of course, we are very far from solving all those points. Okay, we're just doing research on that. Wait, yes? No? Okay. And then of course I will try to see, okay, here on that point, maybe the cloud can be helpful to solve this specific aspect. Okay, so I will first speak about phase A. So this is the teaching phase, and then I will maybe quickly speak about the autonomous mission execution, what I call phase B. So I will speak about that. Yes, well, maybe here during the training phase, maybe the only word you need to memorize is safely here in the slide, because when we do experiments in the lab, you need to know that we are very, very afraid of the robot. Okay, it's big, it's very powerful, so in the end it can kill us. Okay, if we do something bad, the robot, with his arms, can really hurt us. So safety is in general something that we need to consider, but I want to let you know that we really consider it during experiments because it's risky for us. Okay, so, and I invite you to think about it anytime you will do an experiment with a robot. Always think about safety, and remember that you will be near to the robot. So yeah. For phase B, this is mostly the same idea. The fault tolerance is something that must be managed. Okay, so really, at least roughly managed. But okay, faults have a lot of different sources, and I will show you what we consider as energy faults, okay, or sensor faults. I will show you how we can manage this at mission level. Okay, so now I will try to show you how we can implement every different skills that are required for the robot. Because at Liam we mostly do robotics, at least in my department we do robotics, and what is really important for us is control. Okay, so we want self-control. So we want to teach for now long-run movements. So it's just to allow the robot to go to one position to another during the teaching phase. So we need to avoid collision, and what's the main idea in the video I will present is to make the robot capable of following something. So here a simple cat, but we can imagine it can follow a human. We know how to do that right now. So it has to move in the environment, avoid obstacles, keep the vision of the object or people it needs to track, and also it has to manage occlusion in this vision cone. Okay, so maybe sometimes you have some occlusions, and so you need the system must be capable of interpreting the trajectory, okay, estimating the trajectory of objects or people. I will not speak about SLAM, okay, because we do not do a real SLAM at Lyon, and furthermore there are already a lot of things that works not bad, actually, at least in an indoor environment, okay, because we are only indoor for now. So I just put some different SLAM we can use. With Bazaar, we can use the laser, so we can use the laser-based localization. We can use visual 3D SLAM with the camera, and so on. Or we can use also some kind of landmark also with the camera, or simply odometry if you want. Okay. Good. So now this is an experiment we did some years ago. The goal is to allow the robot. Do you see something?
No. Something.
I don't know. Maybe we can turn off the light. Yes, because it's not maybe. So the robot is here, and the first goal is to make it capable of reaching. Sorry, a cart. So the blue cart is in the bottom left corner of the presentation. And of course it needs to avoid obstacles, okay? And we want something really reactive because we don't know the path. During the teaching phase, we don't know any path, okay? So the robot has to be capable of reacting to the movement of the cart itself. So here we move the cart, and the robot maintain a relative pose at best as possible with the cart. But of course the most interesting part is this one. So this is something we implement. So my colleague pulled the cart in a corridor, and the robot automatically maintains this relative pose with the cart while avoiding obstacles. So it can also estimate trajectories of objects it can enter in collision with. For instance, I am here and I will move, but I'm too fast, so the robot knows that my trajectory will not intersect its own. So it will not avoid me, so it continues to go forward, but of course it will avoid collision with the box. Okay, as you may see, the robot is quite impressive, so you don't want it to hurt you, okay, to enter in collision with you, because it's very strong and it's very heavy.
Question.
Yeah?
If in the situation there is not a path possible, how will
good question. For now, to be honest, we do not manage this. We suppose there is always a path. At least we suppose that the path that is followed by that is used by the human or or the cart or the object can be followed by the robot itself. This is an hypothesis. Okay, that does not mean it will take exactly the same path, because it will avoid obstacle, and it will okay, of course, automatically adapt to the shape of the environment. But the hypothesis is that there is the path is reachable for the robot. Okay.
Okay, and the second question is the person in front of the robot walk really quick, and the robot lost.
Yes, so at the moment, so we can interpret the trajectory again. So we can, for instance, when there are occlusion, the robot does not see anything, but it knows that, well, using some classical techniques, it knows how it can, where the human is supposed to go.
Okay.
Okay? Well, it tries to know this. But, of course, if you stay, if the human is not visible during a long time, the estimation is completely bad. Okay, so that's why we want to maintain also the visual connection between the robot and the person or the object, because we want to be as sure as possible that the cart or the object will be followed by the robot. Sorry. But yes, this is not perfect for now. Of course, there are well, how to say? There are situations where we cannot have solution. I think there is no solution. Okay, the person goes, I don't know, it leaves the room.
But I think that you underuse the fact that you're in a scenario that is Industry 4.0, for instance,
Yeah.
that you may have sensors in the environment that provides you with data,
Of
or
course.
even
Of course.
with the 5G networks, things like that will become quite.
I completely agree with that. So for now, of course, in this experiment, we do not manage everything. I really believe that in the future, in this industry, people will be equipped with devices like Google Glasses. Well, I don't know, but they will have wearables on them, and so they will be localizable at any moment.
And the robot will have access to the information.
Yes, so the goal is that the main point is that vision is far, in the end, far more precise for localizing, because with those devices, we know that it's in the room, it's somewhere here, but it's very difficult to localize it precisely.
If you open the door to anything you would need, you could have some localizer on every people, on moving object if there are, and all that communicating with 5G, transmitting their position to the robot. You could have the information right away without
I agree, at least rough estimation of the position, so that the robot can go autonomously.
You could concentrate on the very local or near surrounding problems, not the larger problem of people going to the toilet.
Exactly. But this is the idea behind this experiment. So here for now we imagine that the person just brings the robot with vision in a place where we want it to be. So here how the cloud could help in this part. Well, obviously, maybe so. This is just ideas because we did not implement this. But of course, the most basic one is that the system, the cloud, private cloud system, can provide maps, organization plan of the plants, and of course, it can manage the sharing of the maps built by the robots directly into every robot. So in fact, you need to do the mapping one time, and the system should be capable to share it with any robot. It's not that complicated to imagine. It's something we can already do, I think, right now. Okay, so now let's suppose we brought the robot to a pose, but in fact we want to position it a bit more precisely, and this is very difficult to do with vision. We can try with vision, but it's not that simple. For instance, if we want to position the robot in front of the shelf, okay, where it can take a box containing the parts, yes, we need to be sure that the robot is not that localized in front of this shelf. So we need maybe to position it a bit more precisely. That's why we can imagine using physical human-robot interaction to do that. Okay. So the basic idea I will show you immediately. It's to take the robot and by hand, okay, with your hands, and put it in a very precise pose. This is work done by Benjamin Navarro on using implementing an ISO standard directly into the controller. Okay, so the main goal is to ensure safety again, and the main idea is that the robot limits its velocity anytime it's required to fulfill all the constraints imposed by the ISO 10218 norm. So here is the basic idea. So this is again Bazaar in another configuration, but don't worry, it's always the same. And so the goal is to be capable. So here we just move the arm because we may also want to prepositionate the arms. For instance, if the arms or the camera, we want to prepositionate it a bit more precisely. And then here we can use also pull the robot directly by pulling its arm. We just bring it to a more precise position, and we can reorient. So as you may see, there are little bugs in the.
Is the robot helping, or it's just moved by the force of the people, the person? Okay,
only the forces.
Okay.
Only forces. Of course, in the future we will need to also integrate vision. But here's the goal of this experiment.
You could sense the force and say, okay, he wants me to go that way,
exact.
So I will help by my motors and go that way.
Yeah, only with forces. And we can already have some results using only forces. It's not enough. I will show you this later.
But force, I don't understand the answer. Does this mean that the robot is moving by itself when it is pulled by the guy? Okay.
Yes. In fact, it's kind of simple to understand. When the arm is an extension and near its singular configuration, then you cannot pull it anymore. It can go. So this degree of freedom of the mobile base now activates automatically to follow the human, the forces in the end. Well, I think it's enough. So during this teaching, we also need now once position it. Okay, you can imagine it's more or less in front of the shelf, and now we need to teach it how to grasp objects, etc., etc. Okay, do some manipulation tasks. For now, we have to admit that we only do very simple manipulation tasks. Okay, because it's very difficult. It's a very difficult problem. So it's again based. All I will show you is based. If you're interested in control, it's based on an admittance control scheme. I can answer if you have questions about that. And all the time, again, safety constraints are respected. So now we implement also different kind of experiments. So I will show you some of them. So here the basic goal is to teach drilling or screwing sequence to a robot. So here, just remember that the grasping of the tool is completely predefined. Okay, there is no teaching of that because it's really difficult for now. But we can teach it how to go from one screw to another, and this way we can teach it a sequence. So for this kind of scenario, we can imagine that the camera is placed on top of the robot or on the hand, just to show what needs to be screwed. So here my colleague doesn't do any effort. Okay, all the payload is supported by the robot. It's just drive the robot to the adequate target pose. Okay, this was kind of a simple scenario, so it used also the tactile sensor just to change the mode of the robot. This is another kind of interaction we can implement. So this is just first idea. Then we also focus on two-arm manipulation. So here it's a bit simpler, so we remove the hands because it's very difficult to grasp objects with hands. You have a lot of problems, and this was not the problem in this experiment. So the goal is to implement a global controller, whole body controller, that allow us to do the control with two arms. Also using the mobile base, so everything is now implemented into a whole body controller that we can use the way we want to do many things. So here you can imagine that the robot is capable of simply going from one, executing a sequence of tasks, so moving the object into absolute frame. It can have, you can imagine using this, for instance, for basic manipulation. Okay, we can already do that. One of the interesting part of this work is that we can also define what we call cooperative tasks. So these are the tasks that are referenced to each other. For instance, here the two wrists are a reference to each other to ensure that the internal forces applied to the object are sufficient to hold it. Okay, this is very important, of course. And we can mix them with absolute tasks. So the final goal here is to, you can see that it's capable of moving. I don't know if I can launch again the video. Integrated video, it's not that good. Okay, here you can see, so this is what I spoke about. This is the internal regulation of forces. And the robot moves, and then my colleague will be capable of taking the box and moving it to one part or another. So if you extend to everything I presented previously, we can give an object to the robot. We suppose it's capable of understanding that it needs to grasp it for now, and then we can make it move to a position, and then drive it directly with physical interaction to a target position. For instance, the workbench, where the robot has to put the box. Okay, and this is everything is done now with the sign controller. This is very important for us because we have something very efficient and that already manage a lot of things like avoiding singularities, avoiding auto collisions of the robot, etc., etc. A lot of things that are very boring to implement if you want to do this anytime for each individual task. So here we have one controller that can manage the different parts of the scenario. So here my colleague just move in space the box. Yeah, okay. Okay, that's great. We know how to do that, and we are currently developing all the software and try to make it very easy to use. Well, you can define easily tasks and so on. But it's not enough. For the trick is that the box is very lightweight, okay, and that's simple to manipulate. But in real life, objects have a mass. They have dynamic properties, and that's what we also implement. So the goal is that the controller is capable of automatically estimating properties of the object. Okay, we consider that we know we have a kind of CAD model of the object internally, and so we are capable of estimating. And this way, you can see that the robot is once estimation has been made, the robot is capable of maintaining position of this object while avoiding its dynamics effect. But it's still not enough. Because okay, that's good. The object is now, we can stabilize it, but that does not mean we can correctly interpret the human intention. Because because there are, well, ambiguities of forces at the wrist level, depending on what the human want to apply on the object. For instance, the lever effect is very difficult to interpret if you only have forces in the wrist. So you also need to estimate the contact point between the human and the object. So this is achieved by using vision. We have no other mean, and of course we suppose we know the object, the CAD model. And here, so my colleague just push, and the robot, depending on this contact point, can remove the ambiguities and translate the object. Okay, if now it wants to rotate, it can also rotate, of course. And this is based by coupling vision information. Here, using the OpenPose library, I don't know if you can see it quite easily. Yes. So we have an extraction of the skeleton, and we know the position of object, so we can interpret the contact point of the human hands on this object, and so we can remove all those ambiguities. So yes, now we have something that can be used to manipulate objects, and okay, it's not perfect, it's still research, this is not 100% robust, but obviously since many years now, so some years now, we are progressing very fast. So we are capable of doing a lot of things in a very generic way, and I insist on that point. It's something really important to not have to recode everything anytime you want to redo an experiment. Here, this is a completely generic controller, and we continue to develop this to, well, and put all those basic functionality inside. Okay, on that point, yes, on the object manipulation part, the cloud, in my opinion, can be really helpful. For instance, we suppose here that we know the object anytime. Okay, so during our experiment, it's not that difficult because we just define the file that, okay, describe the object. Okay, simple. But in real life scenario, that's not that simple, because we need to detect the object, and we can imagine using neural network models to do that. Now it works quite well. Well, it works far better than anything else, though. So we can imagine using this to detect the manipulated object. You can think that you can reach well, a confidence of 80 to 90% in object detection if you specialize your neural network for a given amount of objects. So of course, the robot cannot have all the neural network required to understand all the objects in the world. So the cloud obviously should be used to do that. Okay, so I need to detect such kind of object. Okay, I load it into the robot from the cloud, and this is mostly the same for CAD models. Okay, we also need at least a raw estimation of the object models or tools. It's the same. And so here the cloud can be helpful to do that. Okay, well, I need such object, I want to manipulate, assemble such object. Okay, load it into the system. Okay, now we know we can manipulate object for now simply without ends, and ends is still a big problem. Well, generic manipulation. But we also need some way to interact with the robot, to learn, to teach it what is the precise target pose, even in the long run movement phase or in the precise manipulation phase. So here, the basic idea is to use gestures. So it's a first experiment based on gestures detection and gesture detection. So this is not completely innovative, but we wanted to show that it's feasible to control a robot using such kind of techniques. So here the basic idea of the experiment is that you move the robot, so still using the same controller. Okay, now I think you understood. And we positioned the robot to make it reach contact, apply some forces, etc. And then we can use gesture to record the waypoints and the targets, contact, and forces. Okay, we have specific gestures, I don't remember which one. And then after that, we can simply use another gestures to reply the predefined pass that has been learned to the robot.
Can I have a question, please?
Yeah, of course.
How many times do we need to repeat this? Because if we use artificial neural network, I guess we need to have many examples.
To use
Because now we're using the neural network,
yes.
so we need to train the neural network.
Oh yes, of course. Yeah.
So how many examples do we need? How many times we need to repeat this?
No. Yeah. Maybe I need to give an extra explanation. But there is no neural network in the training of the robot. Okay, because I believe that it's not realistic. I really think it won't happen, at least in this scenario. We cannot teach it all position and using neural network to expect the robot to understand the final pass. So what we define are really poses, okay, 6D poses and contacts, etc. We can add extra information in the environment. So there is no learning. So it just memorize, record, if you want, the position. There is no learning for that. There is learning, training is only on gestures. Okay, so we use open pose again to extract skeleton, extract the hand, okay, the box of the hand, and then we teach to the system to recognize here very simple American Sign Language gestures. So there are around 10 gestures that have been learned to the
But
system.
if we put the robot in different scenario or different